Hello, this is the Math 159 Gould Chapter 6 Section 3 video, the second video about the binomial model. In this example, we're going to look at an example for bomber survival in World War II. So a bit of background, in World War II, um, one of the most dangerous places to be was actually in the air. People would volunteer to go into the Air Force not knowing that the survival rate was actually pretty atrocious. In fact, the probability that a bomber would return from a mission was somewhere around, or the people in the plane would return from a mission was about 55.6%. So the probability of success, which would be surviving, i.e. surviving, was about 56%. So 0.556. So interesting thing. Basically, the bomber crews were required to complete 25 missions before they were cycled home. That's originally what was proposed. So a crew had to complete 25 missions to cycle home. And you can actually use the binomial distribution to model this pretty well, because there's a fixed number of trials you had to complete. N equals 25 trials. The probability of success is 0.556. Each trial is independent for the most part, because it's less about the skill of the bomber crew and more about what they were encountering. So success on one mission did not guarantee success on another mission. And there are only two outcomes. You either survived or you didn't. There was success or there was a failure. So using these numbers alone, you can actually start calculating, hey, what's the chance that we would see a bomber crew complete all of the missions? So probability x equals 25 is, oops, there we go, let me type it. So this probability is the probability that a crew completes all 25 missions. Okay, so we're going to switch over to StatCrunch to calculate this. Okay, so n equals 25, probability of success equals 0.556. We want to know the probability that a crew completes all of the missions. And it's pretty tiny. You get this number, which we will switch back to look to see what that number is. So let me paste it. That's the decimal. We move the decimal place 2 over, and it's 0.00042%, which is why they ended up actually reducing the number to 20 missions later, because it was practically impossible to complete that many missions given the low survival rate at the beginning of the war, which is why it is known as one of the dangerous jobs during World War II. It was sort of funny because if you read what people thought at the time, everyone thought like, oh, you're going to be up in the air, like what can happen. If you're interested in it, I highly recommend reading about it. But yeah. Okay, so that's how you calculate that. Let's talk about some other cases that you might encounter. So that was a probability for a fixed or certain number of successes. So this was just saying, hey, there's 25 trials. We want to know the probability of exactly 25 successes, right? All of them are successes. They get to go home. Because if you fail on, mission number 12, you die. You can't continue. And so, the only way to go home was a uninterrupted string of successes. So we can start looking at things that include language such as or more, or less. We did an example with exactly. So exactly is when you say, hey, I want to know the chance of completing exactly 25 missions. So let's look at the or more or less. So what is the probability that a crew had 10 or fewer successes? Actually, well, what's the halfway point with 25? The halfway point of 25 is 12 and a half. So what's the chance that they have 12 or more successes. So this would be a crew that the first 12 were successes, and then they failed somewhere along the way. Okay, so let's write that down. So this is the case where the crew has successes for the first 12 missions, but has a failure somewhere afterwards. So in other words, the first half they're like, oh, we've been successful so far, but then, at some point later, there will be a failure. So as a probability statement, we would say, what is the probability that a crew has 12 or more successes? So if we transfer over to StatCrunch, you would change this here from exactly equals to greater than or equals to. We changed 12 here for the number of successes, and we get this number 0.83. So let me switch over to OneNote. Let me paste that. Okay, that's 83.3% chance. So there's an 83.3% chance that a crew will make it through the first half and then fail somewhere in the latter half. So there is an 83.3% chance that a crew is successful in the first half of the missions and then encounters failure at some latter point. So actually that's sort of like cruel if you think about it. There's a pretty big chance that you'll make it through the first half of the missions and then, die at some point afterwards. So just to give you an idea of like probabilistically what we're talking about here, you have basically a coin flip chance of surviving each of the individual missions, but the probability of making it through all of them because of that is extremely low. So that's the difference between the binomial probability and the individual p probability. So this p here, the 0.556, that's the probability that on an individual mission you will succeed or fail. But because we're talking about a fixed number of trials, the 25 missions, 25 trials, whatever you want to call them, the chance of making it through all of them is what we're calculating here. Or that's what we calculated first. For this one, we're calculating the chance that you make it through the first half and then, encounter failure at some later point. So the chance of that happening is actually extremely high. Okay, so one more thing I want to tell you. So I have some formulas to give you. Okay, so there's a way to calculate I guess you could say that these are formulas for the shape of the distribution. So you might be wondering, hey, what's the mean or standard deviation? So when we're dealing with a binomial distribution, we call the mean the expected value. So remember that the symbol for the mean is mu. So the formula to calculate it is n times p. So this is the expected number of successes. That's why it's called the expected value. Okay, as an example for the bomber missions that we were talking about, the n was 25, the p was 0.556, which means we would expect any individual crew to have about 13.9 successes, which is why in that previous example, like the chance that you make it halfway through and then encounter a failure is pretty high, because with a 50% chance of survival, you're going to get a lot of people who make it approximately halfway through and then start encountering failures, which failures lead to death, and then you stop at that point. Okay, so n times p, the number of trials, times the probability of success, the individual probability of success, gives you the expected number of successes. In this case, 13.9, so you expect people to make it about halfway and then start dying. Okay, and we also have a formula for the standard deviation, which is the square root of n times p, the probability of success, times 1 minus p, which is the probability of failure. And the way I prefer to write that is npq. Q is the probability of failure. Q, I said earlier, is 1 minus p. So this is the give or take. Okay, because not everybody is going to have 13.9 successes. It's going to be give or take a particular amount, right? There's going to be some variance. So if we do 25 times 0.556 times 1 minus 0.556, that's 6.17, and then we need to take the square root of that. Okay, I'm trying to, let's see if it will do it for us. Let's see if we can do square root 6.17, 2.48. Okay, so this means you expect about 13.9 successes out of 25 failures, or 25 trials, give or take 2.48. So you might see successes as low as 13.9 minus 2.48 and as high as 13.9 plus 2.48 normally. So let's calculate those numbers. 13.9 minus 2.48, 13.9 plus 2.48. Okay, so what this is telling you is that given the binomial distribution, if it accurately models the number of successes out of 25 trials, you would expect to see crews have somewhere between 11 to 16 or so successes, right? So you would expect a majority of your crews to make it to the 16 mark. But how many successes are required to actually make it home? 25, which is why so few crews actually survived the war, given the number of missions that they were required to fly. Like this is telling you that it's a fairly rare thing to see a crew have more than 16 successes or fewer than 11 successes, which is why, most of them survived the first couple trips. The issue became later, making it past about 13 successes or 16 successes. Okay, and this is the end of the second chapter 6, section 3 video.